thanks everybody for coming. Can everybody hear me okay in the back? Good. All right. Thank you for coming today. We want to talk about permanent mold and designing for the permanent mold process. I'm Wayne Bennon, Watry Industries. Watry's been around since the late 1950s. We've been doing permanent mold our entire history. I've personally been with Watry for 33 years, so seen a lot of changes around there. We're currently owned by Ligon, which is a private equity firm. They're our current owners. So some of the questions I want to answer today: what is the permanent mold process? And we're not going to delve real deep into the process, but more so you're familiar with it, recognize the needs from a design standpoint, and then understand how the process works in general. And why would somebody design a part for the permanent mold process? There's other processes out there. They may be easier to design for. It may have advantages that we don't offer, but there's certain markets for permanent mold, and we're going to delve into that. What kind of parts are good candidates? You may have a whole suite of part numbers in your facility, and some make sense in sand cast, some make sense in permanent mold. So kind of dive into what kind of parts make sense. And then what do we do? What does Watry do? The permanent mold process in general is we use a steel mold. What we're seeing in the picture there is a female mold half. There's a pouring cup on top. We pour liquid metal into the pouring cup. The mold starts with the parting line horizontal, and then it'll rotate vertical. And in that rotating method, the aluminum runs out of the pouring cup down through the gating system into the cavity. And the part that mold makes is in our booth. If you stop by later, that's a medical industry part. So the metal flows in under gravity by the tilting process. We use a lot of different levels of automation that's matched to the part volume. What you see in the picture there is a rimrock pouring device. It's an automatic pouring device that dips metal and pours it into the mold. So that's done automatically. We also have manual pouring and other methods of automating the pouring process. So the key is using the right level of automation for overall part cost. An exploded view of a mold, the top mold half would be what we call the male mold half. The casting with the gating is shown in the middle. The exploded view shows that there's a sand core here that gets placed right there. That's an expendable core that we set in the mold, pour aluminum around, and then shake out. In this particular case, there's cast-in bushings right here. Those are steel bushings that are placed in the mold. Aluminum runs around them. And this mold also has sliding cores that come together to produce a feature that doesn't draw out in the mold. So it's much like this part I have here, where there's features that wouldn't draw in a typical mold opening. So we have sliding cores, and they're powered by hydraulics. That's the hydraulic cylinder there in the blue. So that's a typical mold. Maybe it's got a little bit more going on than the average mold, in the fact that it has steel cores, steel inserts, and a sand core. Talking about the economics of permanent mold. Very often it depends on the yearly volume. Some parts can work equally well in sand cast, permanent mold, or die cast. And it all depends on the cost of the tooling and the cost of the part. And I've got a little case history coming up with some dollar signs attached to it that'll maybe explain where the volume starts to make sense. So it's a combination of part cost and tool cost. Permanent mold often competes with other casting processes. So in general, permanent mold is in the middle, with sand casting, where there's a wood pattern or a plastic pattern using a sand mold. They typically have the lowest tooling cost, but the highest part cost. Die casting, on the other hand, would have the highest tooling cost, but the lowest part cost, for everything else being equal. Now, there may be compelling reasons why a part can't be made in one process or another. We'll get into some of that later. But if the part could be made in any process, we're in the middle cost-wise, tooling and part price. Investment cast is another option, the lost wax process. Low tooling, high part price, can do a lot of different alloys and very intricate shapes. And then there's a few specialty processes. You don't see a lot of those out there on the floor. Semi-solid, fixo, and squeeze cast. Those are for very unique applications, I would say. An example of a part, and it's the part that's shown in the picture there, which we prototyped for a customer. Just to give an illustration, there was patterns and castings with a little sand cast foundry. Green sand molding, floor molding, nothing very high tech. And the pattern cost of that part was $4,720, and you can see the part cost was $220. A higher volume, more automated sand foundry, Bremer manufacturing, pattern cost was $12,000, but the part cost was almost half, or a little bit less than half. But in permanent mold, the tooling cost was now almost $53,000, but our part cost was under $60. So that kind of gives you an idea. Now, in that particular case, it could not be die cast, so I couldn't give a die cast analogy because it has a sand core in that bent tube area. You can't do sand cores in die casting. They don't stand up to the pressures and the velocities of liquid metal. So that just kind of illustrates the point on sand versus permanent mold. So what's the best deal? The payback on the Bramer would be 913 pieces based on 1 year. That is comparing Watry and Bramer's cost. Between Watry and Duras was 298 pieces. So just looking at it as a simple ROI. There may be design-dependent reasons for specifying permanent mold. High strength, and that's again where there may be some important aspect of the part's application that means it can't be sand cast or can't be die cast. High strength and high integrity. By high integrity, I mean that it's got uniform properties throughout the entire section of the part. With die casting, because we inject under pressure, the air in the cavity doesn't have enough time to exit, and it gets entrained. You get entrained air inside the aluminum. With permanent mold, we'll fill the mold slowly and tranquilly and get the air out of the cavity ahead of the aluminum, which means we get uniform properties throughout the whole part. And they respond very well to heat treat. You can't heat treat die castings because the air will actually burst. It'll blister the casting. Sand casting is heat treatable, has good strength, not as high as permanent mold. With the sand casting process, the aluminum chills slower. So they get larger grain growth, which means lower strength. About 10% lower mechanical strength for the same alloy, same heat treat in sand compared to permanent mold. And pressure tight requirements. Permanent mold is very good at holding parts pressure tight. That part that's shown up there runs up to 4,000 psi. In testing, it operates at 2,500 psi. So basically there's hydraulic cylinders right in the casting and a hydraulic pump, and all the fluid passageways are drilled inside the casting. With permanent mold, we can cast more smaller features than sand casting. Thinner walls, more intricate, less machine stock, weight reductions, therefore cost reductions. And then using sand cores to produce internal passageways. Oftentimes a decision for permanent mold could be based on mechanical strength. That's often the case where they can't get high enough strength in sand or die cast and they'll come to permanent mold. So some of the typical alloys we pour, 319, 356, 357, there's a whole range of different alloys and therefore a range of costs. 319 alloys would be the lowest cost, and 836 and N37 would actually be the highest cost. Some of the mechanical properties I think are listed down there. 37,000 ultimate, 26,000 yield, 5% elongation. And then there's others that are filling in gaps in between there and 319, 319 being the lowest cost. One thing about alloys is the 300 series aluminums are all aluminum silicon alloys with around 7.5% silicon, and that's critical for the fluidity. There's other alloys like wrought alloys, 60, 61, 50, 52. Those are not castable. They have very good properties, but you really can't melt them and pour them into a mold. For lack of fluidity, typically is the main problem. So most common castings are in the 300 series, but there are specialty alloys too. We pour some 443, some 535. So if you have an application for an odd alloy that's not on the list, that doesn't mean we can't do it. We'd have to look at it, consider the design, consider the volume, and see if it's economically feasible. Casting tolerances. There's a very well-published standard out there, the Aluminum Association Standards for Permanent Mold. Now the book that you buy from AA, which you can find it at www.aluminum.org, is actually sand and permanent mold, both in the same book. And our tolerances are tighter than sand cast, but not as tight as die cast. So again, we're in the middle between those processes. To sum it up briefly, and the book goes in way more depth than I'm going to here today, but basic tolerance is about plus or minus 15 thousandths of an inch for features up to an inch. And then you start to gain 2 thou per inch as parts get bigger. And there's a parting line addition, so they're additive. If it's across one parting line, 10. If it's across 2 parting lines, say a sliding core would add another parting line, then it's plus 20 thou in addition to the basic. And there's a lot of good stuff published in that AA handbook, and that's kind of our Bible for tolerances. It also deals with chemistry of alloys, heat treat of alloys, mechanical properties. GD&T tolerancing is in there. I'm talking here with plus or minus, bilateral tolerances, but There's a whole section on GD&T tolerancing in there too, which can be very useful for certain parts. Some of the design considerations, size is one. We do make small parts that fit in the palm of your hand. The majority of our parts are bigger than that. It might be 3 or 4 pounds up to, as it says there, 85 pounds. We cast a full-size basketball backboard for 2 different customers, so that kind of gives you the size of the big end, but they're not as heavy as an 85-pound part. The 85-pound part's just got much heavier wall sections. Minimum wall, around 3.5 to 4 millimeter. It's actually alloy dependent, and I would say it's also part design dependent. If it's very big, getting 3.5 millimeters in the middle is going to be hard. If it's small, 3.5 is doable. And there can be localized areas where it'll be down to maybe 2 millimeters, 2.5, but in localized areas. The aluminum just doesn't stay liquid long enough to fill out if it's thinner than that. Draft angles, and I've mentioned that permanent molds in the middle, tooling price and tolerances and all that. When it comes to draft, we need more than all the other processes. And that has to do with the ceramic coating that we spray on the mold. If you want to come up and have a look at the part after the session here, there's a permanent mold texture on here. It's a mold coating that we spray on the mold. Well, that ceramic coating, if there's not enough draft, will tear away and will wear away. So we need like 3 degrees minimum, and we really prefer 5 degrees. That way the mold coating lasts stable over the long haul. So from a design standpoint, if I'm designing a part, that's a problem, putting draft angles on there. It's a lot easier to design square boxes than tapered walls, right? And machining datums is another area where if we're machining the part, we like to have draft on a datum because it's repeatable and reliable. But machine shops would rather have it be square and not have the difference of the draft angle affecting their CMM check or their location. So draft is a good thing, but it's hard to convince people of that sometimes. Fillet radii, bigger is better, whether it's an inside corner like a fillet or an outside corner. The outside corners on the parts are the inside corners of the mold. If the inside corners of the mold are sharp, they tend to heat check and crack. It affects mold life. Typical mold should last 40,000 or 50,000 pieces, and it could last a good deal longer than that with proper mold design and proper part design. We try to avoid undercuts. You can't see it real well in the picture, but there's an undercut in the wall over here. There are ways to do it. It can be done, but it adds cost into the process. If it can be designed to release in the mold, that's preferable. But all kinds of parts, like this one, has sliding cores here and sliding cores there. So when they're necessary, we do it. Isolated heavy sections. That's something that's very important if we're going to be looking at holding a part pressure tight. And on this part, I've got some slides of the magma coming up, and you'll see what we did. We did analysis on it. It had heavy sections that were in the middle of the part, and we can't get feed metal into those. So the problem was solved by reducing the mass of the part and sort of hollowing it out. I think that's coming up shortly here. Yep. So, and that is this same casting here. Basically, these ears, were planned to be cast solid. And you can see on the inside of the part, it didn't have this coring over here. It's a large part for, I think it's a D9 cat, D8 cat, something like that. And so we ran the magma solidification modeling. And solidification modeling is a computer analysis to see whether you can make a good part before you cut a mold and start sort of learning by error, trial and error. It allows us to really identify, will the casting process we're planning make a good part? And it can avoid some expensive mistakes. It can shorten your effective lead time by getting you so close to making a good part the first day, you don't have to plan for pulling the mold, making a gating change, cooling change, and running a second time. So in this case, we did a baseline. There's no gating on there. It was just to see where does the part want to shrink, where does it have a propensity to shrink. And you can see the colors there. A light, like a white, is going to be pretty much completely shrink. It's going to be solidification, shrinkage. They call it a porosity result, but it's really shrinkage, right, in this case. It's not gas porosity. And as you go down the color chart, it gets to be less and less. Into what's gray is solidified metal, and it's solid and clean. So if we're up in the yellow and the white range, that's a lot of solidification shrinkage. This part has to be pressure tight. It holds liquid on a caterpillar, antifreeze, so it can't be leaking. So looking at that, we said that's a problem, so then how do we fix it? So through the use of magma, and I'm not here to sell magma, but I'll tell you that it helped us a lot on this job. we went in and developed this coring that you see up here, and it's modeled in there. And now we've got shrinkage porosity that's way down into like the red range. One of the unfortunate things with casting is every casting has porosity. It's a matter of how hard you look to find it. We don't make totally clean parts, and I don't think really any of the aluminum foundries do. But the trick is having the porosity which develops in solidification in areas that don't cause a problem in the application. So sometimes there may be a feature added just to be there as a feed passage, which is what some of this is. That doesn't serve a function in the end use of the part, but it's there to provide a feed passage to the area that was shrinking. That's the kind of thing without magma, we wouldn't have any idea to do that. You can use experience and best guesses to get pretty close, but magma helps me, you know, as a sales guy, go back to the customer and say, you need to make this change. You know, add some metal in the part. Well, why? Because we can show you on magma that it has the proper effect. Although we added metal here, we reduced metal here and here, and see that we cored both of these holes now. In the previous slide, only one was cored. So the net effect was, in the end, the part was lighter, not heavier, and we got rid of the shrinkage. So, and that's the perfect situation where you solve the problem by saving money as opposed to solving the problem by throwing money at it. Sand cores. Sand cores would be used to produce a passageway that can't be drafted out in steel in any way. One thing about Watry, we don't make the cores, we buy the cores. We're very good at permanent molding. There's people who are very good at making sand cores. So instead of duplicating that, we simply go out and buy the cores. We get them from Supreme Cores, but there's other core vendors too. Cores do add complexity and add a level of quality concern that has to be, you know, taken into account in the process FEMA. It does require more time. If we're quoting a part for you that has a sand core in it, takes me longer to get that done because I have to go to somebody to get pricing on it. And really need 3D models anytime there's a sand core. Most of you are on some kind of a 3D solid modeling system, and sending us a step file, an IGES file, Parasolid is really necessary to look into sand cores. I'm not going to really go into the whole core blowing process, but it's a chemically bonded sand, and then the sand holds together like a cement block, so to speak, and you pour aluminum around it, and then shake it back out of the part. Another thing that we do a lot is take over molds from other foundries. So if you have a mold that somebody can't make good parts, you know, give us a call. We've got, well, one in our shop right now that we're taking over from another foundry, and we did one earlier this year. So there are some standard mold designs out there. The picture's not so good, but that's a Stahl, which is also a Ligon company, used to make and sell machines. They were Stahl casting machines, 18 by 24 size. It's very common to have a mold set up for that. We can take those molds and drop them right in our machines and run them with no retrofitting at all. If it's bigger, there may be some retrofitting required. We really need to have a look at the mold. Oftentimes, though, taking over an existing mold is like buying a used car, and you're getting somebody else's problems in the process. So it may need gating changes, it may need process changes to make a good part. In general, we take over a lot of molds, and we find out there's usually a good reason why they're exiting the other foundry. And with that, I'm pretty well done. And if there's any questions, I handed out the sheet on permanent mold. It sums up a lot of the things I talked about here. There's not the things concerning cost on there, but the tolerance, the alloy, the size of the parts is on that little 2-page flyer there. So, any questions or any other topics you want to bring up?